So in this video we're going to look at the Euclidean algorithm, which is a method for finding the greatest common divisor of two integers. So firstly, just some notation. So if we have two integers, which we'll call m and n, then we denote the greatest common divisor as GCD, and then we put brackets of m and n. So you would read that as greatest common divisor of m and n. And I'll write this out once in full. So the G is for greatest, the C is for common, and then the D is for divisor. So, not division, divisor, divisor. So a divisor is an integer that divides another number. So you could have a divisor of m, you could have a divisor of n. A common divisor is something that's a divisor of both m and n, and then the greatest one is the biggest one, the most far one along in the positive direction in the ordering on the integers, the standard ordering of the integer number line. So to illustrate this better, I'm going to take an example. So we'll take 20 and 36. So you can view, if you like, m as 36 and n as 20. And for each of these numbers, I want to write out all of their divisors. Then we can see which ones are common to the two, and then we can finally see which one is the biggest of the common divisors. So let's start with 20, a slightly smaller number. So firstly, we don't need to consider any integer that's bigger than 20, because if you consider something like 21, the first integer that's bigger than 20, if you multiply it by 0, you get 0. If you multiply it by 1, you get 21. If you multiply it by any negative numbers, it goes off in the negative direction. If you multiply it by anything bigger than 1, it's going to be even bigger than 21. So there is no integer that you can multiply 21 by to get 20, and indeed the same logic is going to hold true for all of the other integers bigger than 20. So we don't need to worry about them. 20 clearly divides 20 because 20 times 1 is equal to 20. So 20 and 1 are both divisors of 20. Then if we go up, is 2 a divisor of 20? Yes, it is, because 2 times 10 is equal to 20, so 10 is also a divisor of 20. 3, no joy at all. 4 is a divisor, and it multiplies by 5 to give 20, and there's going to be nothing in between these that is going to multiply to give 20, because there's no corresponding thing over here. You know, if you had something in between 10 and 20 that was multiplying to give 20, the thing it was being multiplied by would have to be in between 1 and 2. So we can be pretty confident in our list here, and in fact that's the complete list of all of the positive integers that divide 20. 0 doesn't divide 20. If we want to make a complete list, we need to now include all the negative ones as well. So we just put all the negative versions of these. So -1, -2, -4. It looks as though we're going to run out of space. Tragically, I might rub out this 20 so we have some more space. So -4, -5, -10, and -20. So that's the list of all the divisors for 20. Let's do the same for 36. So of course we'll have 1 and 36 again. Then we'll go up to 2. 2 is also a divisor, and it multiplies by 18, so the next one down is going to be 18. 3 works as well with 12. And again, I'm skipping all these numbers in between, again by the same logic that, you know, if there was something in between these that was multiplying to give 36, there would have to be something in between these that it was multiplying by, which there isn't. Then 4, 9, 5 doesn't work, 6 works, and it's going to be the one actually in the middle because it multiplies by itself to give 36. So those are all the positive ones, and then we could put all the negative ones as well. -1, -2, -4. Sorry, I missed one. We need -3 there as well. -3, -4, -6, -9, -12, -18, and -36. So those are all the divisors, integer divisors of 36. And now what we can do is look at the common ones. So let's underline in some colour the common ones. So these are all common. They're all there. 4 and negative 4 are common. 5 isn't common. 10 isn't common. 20 isn't common. So we're out of them now. So the ones underlined in blue are all common divisors of 20 and 36. The greatest common divisor is then, look at this list, and we could copy this list out now. So it's -4, -2, -1, 1, 2, 4. That's the list of common divisors. I'll call them the CDs. And then all you do is you go to the most positive ones. You go up and up in the ordering to the highest one, and that is 4. And that is then what we would call the greatest common divisor of 20 and 36. Or you could write it the other way around, GCD of 36 and 20. Good, so that's the meaning of greatest common divisor, explained with an example. Let me also just highlight that this works for negative numbers as well. You know, if we were looking at -20 and 36 and thinking about what the greatest common divisor of these two numbers is, if you wanted to find all the divisors of -20, it's actually exactly the same as the divisors of 20. So the list of the divisors is exactly the same as we have here. 36 has remained the same, so its divisors are all here. So again, we'd have the same list of common divisors, and the greatest common divisor is still defined to be the one that's highest up in the positive direction. You don't suddenly change the meaning to be the most negative one because you've got a negative number. It still remains the case that you want the one that is highest up in the positive direction. So the GCD of 36 and -20, or -20 and 36, is still going to be equal to 4. And that holds true even if you make both of them negative. So if you have both of them now negative, you still don't change it to -4. Again, if they're both negative, these list of divisors remain the same, the list of common divisors remains the same, and you don't suddenly decide that you want the one most in the negative direction because you've got the negative numbers now. You still define it as the one that is most in the positive direction, which is 4. So the answer to this is also 4. So that then is the definition of the greatest common divisor. I hope that is understood. So let's now talk about the Euclidean algorithm. So this is a really brilliant method for finding the greatest common divisor of two integers without having to do all of this work that we did here, which wasn't too much work for 20 and 36, but you can imagine if these were huge numbers, if they were 7-digit numbers, this would be a lot more work writing out all of their divisors and then working out which ones are common and then finally finding the biggest one. The Euclidean algorithm is a much cleverer method for finding the greatest common divisor of two integers. So I'm going to illustrate how to do this firstly with the example of 36 and 20, and I'll show you that you get 4 with it. And then we'll talk about the reason this actually works. And it's beautiful, the reason this works. I really, really like this. So all of this algorithm uses Euclidean division. So I have a previous video in this playlist on number theory on Euclidean division. If you're not familiar with the concept of Euclidean division or division with remainder, the fact that you can always divide with remainder in the integers, please watch that. So this is how you do it. You take the bigger of the two numbers, the one with the larger modulus. It would be more important to specify that we're talking about moduli in the case where we've got numbers which are potentially negative. So if we, for instance, had 20 and -36, it would then be important to specify that we mean the number with the biggest modulus, which is the -36. But in our case, it's just the bigger number. So 36, and then you write it as using Euclidean division with your other number, 20. So we're going to write it as some quotient times 20. Now, the quotient we're going to need is 1. So 1 times 20 plus some remainder, which is going to be, not 14. I've done some terrible mental arithmetic there. 16. And Euclidean division tells us that we can do this. We can pick a Q here and an R here, such that this remainder is a positive number, or at least a non-negative. It might be 0. So R is going to be greater than or equal to 0, and it's going to be less than the size of the modulus of this number, so less than 20 in this case. So that's what we've got here. We've done it. We picked Q as 1, and then we have this remainder of 16, which certainly satisfies that inequality. Now, for reasons that I will explain in more detail in just a moment, it turns out that the GCD of 36 and 20 is going to be the same as the GCD of 20 with this remainder number here which you get from Euclidean division of 36 by 20. So actually, finding this GCD is the same as finding this GCD. Now what we can do is we can apply this fact again. We can say, okay, now let's make the problem even simpler. We now want to find the GCD of 20 and 16. So what if we use this same brilliant fact again? We write 20 as some quotient times 16 plus some remainder. Then we'll know that our GCD is going to be the same as the GCD of 16 and that new remainder. So doing this, we write 20 is equal to some quotient, which again will have to be 1, so 1 times 16 plus some remainder, and Euclidean division tells us that there's a way of doing this such that that remainder is greater than or equal to 0 and less than the size of 16, so less than 16. And of course this is the way of doing it. You make Q1 and the remainder 14, and now we can conclude that this GCD is going to be the same as the GCD of 16 and 4. And then finally what we note is now that 16 is just a direct multiple of 4. It's 4 times 4. Therefore, the GCD of these two must be 4, because it can't be bigger than one of the numbers. You know, if you're considering the GCD of two abstract integers, m and n, this cannot be bigger than the size of those two integers. It's guaranteed to be smaller than the modulus of m, well, less than or equal to rather, and it's going to be less than or equal to the modulus of n. It can't suddenly be bigger, because otherwise there wouldn't be any way of multiplying it to get this smaller number. So for instance, if it was 5, how would it possibly be a divisor of 4? Because 5 times 0 is 0, that's not 4. 5 times 1 is 5. 5 times negative numbers goes to negative numbers. And then 5 times anything bigger than 1 is always going to be bigger than 5. So nothing times 5 is going to ever give 4. And that same sort of argument holds true for all numbers bigger than 4, that they can't possibly be divisors of 4. So to be a divisor of something, you have to have size smaller than or equal to the thing you're dividing. So it can't be bigger than 4, but actually because 4 is a divisor of 16, 16 is a multiple of 4, then 4 divides 16, and of course 4 divides itself, therefore you can conclude that 4 is going to be the greatest common divisor. So this greatest common divisor of 16 and 4 is going to equal 4, and because I know this is equal to this, and this is equal to this, and this is now equal to 4, I can then conclude that my initial GCD of 36 and 20 is equal to 4. So the crucial argument then, the whole thing that this is all based off, is this fact that you can replace the GCD of two numbers with the GCD of the smaller number and the remainder that you have here. So let's talk through why that works, and we'll do it in the more abstract context. So we'll go back now to m and n, our integers, and we're trying to understand why this fact about the GCD of m and n is going to hold true. So firstly, let's assume that one of them has the larger modulus, and we'll assume without loss of generality that it is m that has the larger modulus. It could be the case that they both have the same modulus, but in that case they're either both the same number, in which case their GCD is clearly that number, or one is positive and one is the negative version of that number, so you'd have n and negative n. Again, clearly the GCD is the modulus of n. So, you know, if you had GCD of 7 and negative 7, the GCD is 7. GCD of 9 and negative 9, the answer is 9. So it's very easy to find the GCD in the context where both of the numbers have the same modulus. So we might as well just look at the case where one is bigger than the other in modulus. So we'll say m is the one that's bigger in modulus. Now, of course, m could still be a negative number, n could still be a negative number, but we're saying that modulus-wise, m is bigger than n. Then what we want to do is write m as some quotient times n plus r, where that remainder is going to be non-negative and less than the modulus of n in size. And Euclidean division guarantees us that we're going to be able to do that. What we now want to understand is why it is the case that the GCD of m and n is equal to the GCD of then n and this remainder r. Why is this true? Now, note that one of the cases, of course, is that r is equal to 0, in which case this is nonsense. This doesn't hold true. But if r is equal to 0, that means that m is a direct multiple of n. n divides m. And in that case, you can easily find your GCD. It's just going to be the modulus of n. If n is a negative number, then it will be the positive version of it. If it's a positive number, it will just be it. So in the case when the remainder is equal to 0, that's simple. You can easily find the GCD. So we're not interested in that case. And in fact, I'll delete this is equal to here. We're really only interested in the case when the remainder is non-zero, so it's going to be strictly positive. We want to understand why this is going to be true in that case. So the reason it's going to be true is the way we can show this is we can show that any divisor that is a common divisor of m and n is also going to be a common divisor of n and r, and anything that is a common divisor of these two is going to be a common divisor of these two. So in fact, if you were to write out the list of common divisors for these two, you'll get the exact same list as if you were to write out the common divisor for these two. That's what we need to show, and then we'll know that the greatest common divisor is therefore the same, because if they have the same list of common divisors, the one that is the most positive, the biggest one, is going to be the same in that list. So that's what I now want to show you. I want to show you that if you have a divisor d that divides m and it divides n, then we have a biconditional between that and d dividing n and d dividing r. So if this is true, this is true. If this is true, this is true. That will then mean that the common divisors, any divisor of these two is a divisor of these two, therefore, and vice versa. Therefore, the list of common divisors is going to be the same. So let's go through why that is the case. So firstly, we'll do the forward direction. Why does d being a common divisor of m and n mean that d will be a common divisor of n and r? So obviously, if d is a divisor of n, then we've got this bit satisfied. So we just need to prove that d will be a divisor of r. Well, here is the equation for r. Just rewrite that. R is equal to now m minus q times n. Because d divides m and d divides n, we can write m as some integer which I'll call z1 times d, and we can write n as some integer which I'll call z2 times d. Just substitute those in now, and we get r is equal to z1 times d plus, and we'll swallow that minus into the q, so we've just got minus q there, times z2 times d. Just factor out the d now, and you've got z1 plus minus q times z2 all multiplied by d. Q is an integer, negative q is an integer, negative q times z2, z2 is an integer, so that will be an integer, this thing, and then we're just adding it to another integer, so this is all going to be an integer, so you've just got some integer times d. That's the exact definition of d dividing r. So from these two, I've got this, I've clearly got this, so I've done the forward direction. Now let's do the backwards direction. So let's understand why if d divides n and r, so d is a common divisor of n and r, it's also going to be a common divisor of m and n. So it's clear, obviously, again, that it divides n because that's there. Let's just prove that it divides m. Well, it's exactly the same proof. We just use this equation. It's actually even simpler because we don't even have to rewrite the equation. M is just going to equal qn plus r. From the fact that d divides n, we have that n is equal to, and we'll keep our notation the same, so we'll use z2 times d here. And then from the fact that d divides r, we have that r is equal to, let's say, z3 times d. So just substitute those in now. We'll have that m is equal to q z2d plus z3d, and then just factor out that d, qz2 plus z3 times d. Again, the integers are closed under multiplication and addition, so this thing is going to be an integer. So we've got some integer times d, which is exactly the definition of d being a divisor of m. So I hope what I have just convinced you there is that any common divisor of m and n is also going to be a common divisor of n and r, and any common divisor of n and r is also going to be a common divisor of m and n. So they're equivalent lists. If you list out the common divisors of these two and the common divisors of these two, you'll get the same list. And therefore the one that is the biggest in that list is going to be the same. Therefore you can conclude that the GCD of m and n is the same as the GCD of n and r. So let's go back to our algorithm. So remember, we have m and n are integers, and we're trying to find the GCD of m and n. Now, we might as well assume that they don't have the same modulus, because if they do have the same modulus, the problem is trivial. So one, therefore, will have a bigger modulus than the other. We're saying we'll call the m1 the one with the bigger modulus, and n will be the smaller one. We can then write m as a quotient times n plus a non-negative remainder. Now, if the remainder is equal to 0, then again, finding your GCD is pretty trivial because m is a direct multiple of n in that case. And your GCD will just be the modulus of n. So if n is a positive number, it'll just be that n. If n is a negative number, however, it'll need to be the modulus of it, the positive version of it. Now let's just think then about the case when the remainder is not 0, so it's some positive number, so greater than 0, less than the modulus of n. And we know that we can find such an r from Euclidean division. What this now tells us is that actually the GCD of m and n is the same as the GCD of n and r. So we can reduce our problem to finding the GCD of n and r, and this is better. The reason this is an improvement is m was the biggest number, remember, in modulus. n was a smaller modulus number, and r is a smaller modulus number still. Also, what's brilliant about r is we can guarantee it's a positive integer, and we like positive integers. It is easier on the head. So we've got rid of some big modulus number that was potentially negative, so it was potentially very nasty, and we've replaced it with a non-negative integer, a positive integer, that is of smaller modulus than it. So this is a better problem. Now, what we do is another round of this. So to find the GCD of n and r, I'm now going to label this R1 because, of course, we're about to do Euclidean division again to get new quotients and new remainders. So let's subscript these Q1 and R1 here. So now we can take n and we can write it as some quotient, which I'll call Q2, times this number R1, plus another remainder R2, where we know that R2 is going to be greater than or equal to 0 and less than the modulus of R1, but R1 is a positive number, so we can drop the modulus. Now, in the case that R2 is equal to 0, bingo, that means n is a direct multiple of R1, therefore the GCD of n and R1 is just equal to R1. Remember, it's a positive number, so I don't even need to say the modulus of R1. So we're done in that case. If R2 is not equal to 0, then we can now conclude that the GCD of n and R1 is reduced to finding the problem of the GCD of R1 and R2 using the exact same logic that we applied here. This is now equal to this problem. And this is a simpler problem still, because R1 was smaller in modulus than n, R2 is now a smaller number than R1, and brilliantly, R1 and R2 are now both positive integers. N could have been a negative integer. Again, nasty, not nice on our brains. But now we've reduced the problem to two smaller size integers that are both positives. And then you continue this process on until eventually one of these numbers that you've got is going to be a direct multiple of the other. So finding the GCD of R1 and R2, you'd again go R2 is equal to Q3 times R1, sorry, not R1, sorry, I've confused this. Forget what I just wrote down, that was completely wrong. You'd say R1, which is the bigger one, is equal to, this is going to be Q3 times R2 plus R3, where again R3 is going to be greater than or equal to 0, but less than in size of R2. And again, if R3 is equal to 0, brilliant, that means that the GCD of R1 and R2 is just equal to R2. If it's non-zero, then again you're going to change the problem and it will be the GCD of R2 and R3. And you just continue this on until eventually you get down to it being the case that the smaller one, the one with the bigger subscript, is a direct multiple of the previous one. And at that point, you'll be able to conclude that this one is your GCD. So for instance, if the next equation was that R2 is a direct multiple Q4 of R3, then brilliant, R3 is then going to be our GCD. So to finish, I think I'll do an example, and we'll take an example with difficult numbers, or numbers that look scary. We'll make them negative. So we'll do the GCD of minus 120 and minus 36. So minus 120 is the bigger modulus one, so we'll write it as a quotient of the other one, minus 36. So we need to write it as something times negative 36. So you might think that we would use 3. But the problem is if we just multiply it by 3, we'll actually get something that's less negative than minus 120. Remember, we want a positive remainder ideally rather than a negative remainder. So if I was to use 3 times minus 36, I think that gives minus 108. So you'd need a negative remainder of plus minus 12. All of what I've told you so far works with positive remainders. However, all of the arguments that I have done in terms of why the GCD of M and N is the same as the GCD of N and R, they all hold true if you used the negative remainder version of Euclidean division. They work just as well as for the positive remainder definition of Euclidean division. However, just because our brains prefer positive numbers, I've done it all in terms of positive remainders. So we'll continue in our example to work in terms of positive remainders. So we'll scrap this, and instead we'll write minus 120 as 4 times minus 36, which will give minus, gosh, maths, minus 120 is minus 30 times 4, and then 6 times 4 is going to be minus 24, so that overall gives minus 144, so you have to add on 24. So there's the positive remainder, which we could have worked out, of course, because 24 plus the modulus of this one makes 36, so the remainders are kind of the complements in size of each other, the positive and negative remainders. Okay, brilliant. So now what we can conclude is that GCD of negative 120 and minus 36 is the same as the GCD of minus 36 and 24. And you can see, beautiful, we've got rid of a horrible big negative number and replaced it with a lovely much smaller positive number. So it's going rather wonderfully. Let's continue on. So now what we'll do is we'll do the same thing for minus 36, which is the bigger modulus number. So minus 36 is going to obviously be minus 1. Oh, actually, no, I'm about to make the same mistake as I just advised you not to make. So remember, we want to do it all in terms of positive remainders. So we need to do minus 2 times 24 to get more negatives so that we can then have a positive remainder. So that will be minus 48, and we need to then add on 12 there. So we can now conclude then that GCD of negative 36 and 24 is going to be the GCD of 24 and 12, and now you can see that 24 is just a direct multiple of 12, so it's 2 times 12, so that's where you stop. We now know that this GCD must be 12, because it divides 12 and it divides 24, and nothing bigger than that can be a common divisor of these two, because it can't divide 12. Nothing bigger than 12 is ever going to divide 12, so you've done. you've got to this point where you can write one of these remainders as a direct multiple of the other, and that completes the Euclidean algorithm. So 12 is the greatest common divisor of these two numbers, and you can see it's a common divisor of both of them. 12 times negative 3 is minus 36, 12 times negative 10 is negative 120, and it is indeed the greatest common divisor. So with that we will finish. I hope that has made sense.